Hey, everybody. So I wanted to do a quick example to kind of bring together some of the ideas that we've been going over in these first few videos. Um, and so here I've got an example of a definite integral. Um, so I want to compute that, right? And we're going to use the fundamental theorem of calculus to do that. On the way there, we're going to do a little bit with indefinite integrals, which is just a symbol we use to represent antiderivatives, right? Because there's this really deep connection we see between the fundamental theorem between our definite integrals and antiderivatives, and so that this connection makes sense to use this as an antiderivative symbol, right? So let's just say what I or write what I mean by that. So the big idea when we want to compute a definite integral, right, is we take we evaluate an antiderivative of the function, the integrand of the function in there at the endpoints, right? So that's all I've said here is that in order to evaluate this definite integral, right, provided f is continuous, all those little things we need, but that's in another video. We can evaluate it by taking a look at the antiderivative, any antiderivative of lowercase f, and evaluating the difference at the endpoints of the interval, right? And so because of this connection between antiderivatives and integrals, we also use this symbol to mean, let's just say means that capital F of x is an antiderivative of lowercase f, right? In other words, capital F prime is equal to f, okay? And then let's just throw in here, excuse me, let's just throw in here our plus c. Whoops, I didn't mean to change all those colors. Right, so we add this little extra there because when you take the derivative of this whole function at capital F of x plus c, you still get the antiderivative because in the derivative that constant goes away. Okay, so here's our two big ideas. So in order to compute this definite integral, in other words, in order to use this fundamental theorem, this that I have written on top here, we need to find any antiderivative of this function t squared minus 1, 2 minus t. Okay, now how do we do that? So we've got to come up with something that whose derivative is what we're looking at here. An easy mistake would be to kind of look at these two pieces individually. If I let's just do a little bit of scratch work off to the side here. If I think about t squared minus 1, a function whose derivative is t squared minus 1 would be t cubed minus t. So you can go ahead and take that derivative and you'll see that you get exactly t squared minus 1. And if I wanted to find something whose derivative was 2 minus t, that would be 2t minus 1/2 t squared, right? And it's true that if I take the derivative of this the first parentheses here, I'll get the first parenthesis here. And if I take the derivative of this here, I'll get, of the 2t minus 1/2 t squared, I'll get 2 minus t. The problem is, that's not how derivatives work. If I were to take the derivative of this thing, I'd have to use the product rule, which would make it much more complicated than what we have here. And so this is an easy mistake to make. It's not true. This is not the correct, this is not the antiderivative of this function. You can go ahead and take that derivative using the chain rule to see that it doesn't quite work. So what can we do? Well, what we can do is a little bit of algebra. If I expand this expression, I'll get, let's just multiply it out. T squared times 2 is 2t squared. And then I've got t squared times negative t is minus t cubed. And then I've got minus 1 times 2 is minus 2. And then I've got a plus t. And that expression is a simple sum of power functions, right? It's a polynomial. And these are among the easiest derivatives and antiderivatives to take, because remember our properties of integrals. If when we take the integral of this whole thing, we can take each piece one at a time, and then we'll be able to use our reverse power rule, right? The same rule that I did up here to get this wrong answer, but now we'll do it in the correct way. So I'll go through that in a little bit of detail. So what I'm going to do, I'm not going to worry about the bounds of the integral. First, I'm just going to look at taking this antiderivative. I now know I can accomplish this, and I'm going to kind of rearrange this as it doesn't matter. I'm just going to leave it as is. 2t squared minus t cubed minus 2 plus t dt. Okay. Now I'm going to go through this step by step, since this might still be fairly new to us. The first property of integrals I'm going to use is I can turn this into 4 separate integrals. And plus t, right? So there's a rule about integrals separating over addition and subtraction in this way, so I can separate them this way. I can also pull these constants out front. That's another one of our rules, that when we have a constant times a function, we can simply move the constant out front. Just gonna write, this is a little bit weird to write, but just for consistency, I'll write that. Okay, so now I've got 4 fairly simple integrals to compute here. Let me remind us of one of our rules that I'll be using. So let's get rid of this wrong answer. Here's our antiderivative rule that I'm going to use. Right? If I have the antiderivative of x to the n, this is going to be x to the n plus 1 over n plus 1 plus c, as long as n is not equal to -1, right? Then we'd have to do something different, but we'll save that for another time. So this was sometimes called the reverse power rule, or the power rule for integration, something like that. But you can see what it is. If you remember your power rule for differentiating, take the derivative of this. N plus 1 comes down front. It cancels with the n plus 1 in the denominator. We subtract 1 from the exponent to leave us n, which is exactly what we have here. We're undoing, we've got reverse differentiation and differentiation. We get back to what we started with. Okay, so I've got 2. I can apply that rule here. So my exponent goes up by 1, and I get that same number in the denominator. Then I've got the same thing here. The exponent goes up by 1, and I get that number in the denominator. This one's a different rule. The antiderivative of 1, you could think of it as t to the 0 if that helps, but you can just remember what function has a derivative of 1 is just t, and we've got this -2 up front. And then here we've got a t with a 1 as its exponent that we don't write. And maybe I'll just write this. For some reason, I prefer it this way. It's really bugging me that they're not in order from highest to lowest exponents, but I'm gonna let it go. Okay, so there is our antiderivative, right? That plus c is because it's a family of functions. Any number on the end there, if you take the derivative of this, you'll end up with what we have, right? If you take the derivative of all this, and I encourage you to do this, check this result by taking the derivative, and then you could factor this to get back to what we started, right? Well, if you add a number on the end, no matter what that number is, when you take the derivative, it disappears. And so it doesn't change anything in terms of our antiderivatives to have any number there. So we usually write plus a constant, and C is the traditional letter to use, okay? So now that we've found an antiderivative, we can apply this fundamental theorem, right? Because that's what the fundamental theorem tells us. If we have an antiderivative, we can apply it. We can take the difference of we can evaluate it at the endpoints and take the difference. So let's call this antiderivative f of t, capital F of t, 2/3 t cubed minus 1/4 t to the 4th minus 2t plus 1/2 t squared. Now, here I'm going to leave the c off because when we evaluate definite integrals, we don't need a particular antiderivative. We need any antiderivative. In this case, I'm going to take the one that's the simplest, where this constant is just a 0. So I'm just using this. So I'm going to need f of 3. Let's write this out. According to the fundamental theorem, now that I have this f, my definite integral can be evaluated this way. Since this is pretty big and ugly, I'm going to compute these each separately. So f of 3 is equal to 2/3 times 3 cubed minus 1/4 3 to the 4th minus 2 times 3 plus 1/2 3 squared. So let's see what we get here. I can cancel this with one of these. So 3 squared is 9 times 2 is 18. I'll get 1/4 3 to the 4th is 81. I've got minus 6 plus 9 halves. Oh, this is a bit ugly. 18 minus 6 is 12. I've got minus 81/4 plus 9 halves, which is 18/4. So let's see, 12 in terms of fourths is going to be 48/4. 81 minus 18. We've got 63. So I've got minus 63/4 or negative 15/4. Okay. I hope I did all that right. If I made an error, you're free to correct me. Then we've got to compute f of 1. This should be a bit easier. Sorry, I pushed f off the screen. So all those t's are just going to be a 1. So we're going to have 2/3 minus 1/4 minus 2 plus 1. So I guess we can use 12ths. So I've got 8/12 minus 3/12. And then minus, I've got minus 2 plus 1 is minus 1. So that's minus 12/12. So this looks like it's all going to be negative. What do we got? 8 minus 3 is 5. Minus 12 is negative 7/12. Okay. So now, finishing up our integral from 1 to 3 of t squared minus 1, 2 minus t, remember, is f of 3 minus f of 1, or negative 15/4 minus 7/12, minus negative 7/12 is plus 7/12. And so now we'll have minus 45/12 plus 7/12 is going to be a negative 38/12 or negative 19/6. So barring any computation error, I probably should have worked that out ahead of time, but maybe I screwed something up in there. This should be correct. And the big point is how this connection between the definite and indefinite integrals. Okay, that is it for this one. Thanks, everybody. I will see you in the next one.